Hey, so I'm Steve Newman. I'm a career engineer and founder of Scalyr, an analytics service for event data designed for observability and custom analytics. Prior to Scalyr, I was part of the team that created Google Docs, and today I'm going to talk to you about the journey from a three-person startup to Google Scale, and the observability challenges that we faced along the way. And how those challenges are now widespread throughout the industry, and the unique architecture that we've created at Scalyr to address those challenges. So, modern architectures based on the cloud, microservices, technologies like this generate an enormous amount of event data. These technologies enable enormous scale, the enormous scale that modern applications run at. And that scale generates a lot of operations and a lot of data. Furthermore, that's sort of the width of the data based on the amount of traffic that these applications are handling. In addition, you have sort of these tall architectural stacks now, where you have applications composed of services built on something like Kubernetes running in the cloud. And that very tall stack creates more data relative to what the application is doing, and so the combination is just a geometric increase in the amount of data that modern applications generate. And this creates real challenges for observability solutions, which often struggle to handle the amount of data while maintaining reasonable performance and reasonable cost. We call that three-way trade-off between scale, cost, and performance the golden ratio of observability, and that ratio is really at the heart of the challenges with modern observability. The architecture that we've created at Scalyr raises that bar by an order of magnitude. So let me start by telling a story. On the journey from Writely to Google Docs to Google Drive, we had to build an indexing system to allow people to find their files in Google Drive. And we had done a bunch of analysis to cost out, how much resources this indexing system was going to take to run, and we started deploying it with production data, and we found that the indexing step, building and creating the index, was using roughly 10 times more CPU than we had anticipated. And even at Google, we weren't able to get enough servers to handle the load. It was threatening to hold up the whole Google Drive launch. It took us months of increasingly, frankly, frantic investigation to finally suss out what was going on. And so to understand this, the basic math of the system was that the CPU cost to index one file was the product of the size of that file, how frequently the file was updated, and the number of people the file was shared to. Now, the typical file was pretty small, wasn't updated all that often, and actually typically wasn't shared at all. And so that overall indexing cost would be modest. Now, every now and then you'd have a file that's larger, or a file that's updated more frequently, or maybe a file that's shared to a bunch of people. And these would cost a little bit more, but still not all that much, and there weren't that many of them. So this kind of still fit within our projections. So what we hadn't realized, and finally took all those months to unearth, is that there were a small number of outlier files. Like for example, literally there was a sign-up sheet for the Google company picnic. And this file, it had the name and email address of every Googler in Mountain View. It was shared to every one of those people. And it was constantly being updated every time someone added themselves to the sign-up list. So the size update sharing product for that file was enormous, and just maintaining the index for that one file took an enormous amount of CPU. There were about 100 files of this nature that between them were accounting for the majority of index update cost across all of the billions of files in Google Drive. And once we finally unearthed this, we were able to do something about it. But until we got to that point, we were just helpless. Now, if we'd had a log of all of the updates to the index system, it would have been easy to spot this issue. But all we had were kind of pre-digested metrics that gave us a high-level view into the indexer performance. And metrics really only let you investigate problems that you've anticipated in advance, which by definition meant that they were of no help here. Observability was a challenge throughout the Google Docs and Google Drives projects. I've talked about how both the scale at which we were operating and the use of modern architectures just generated an enormous amount of event data. And if Google couldn't handle the scale of the telemetry, then no one was going to be able to. So we realized that these problems were really destined to spread throughout the industry as more and more companies moved on to modern architectures. They were going to be faced with these same kinds of challenges. There are a myriad number of data sources that need to be accounted for. You have individual servers generating data. You have often microservices. You have systems running in the cloud. You might be using Kubernetes. You have IoT devices. So all of these things are generating data, and they're ultimately serving a variety of applications and outputs. So, we have dashboards and metrics to provide a high-level view of the system. You have alerting and monitoring to notify of unusual conditions. You have analysis and data exploration, and often this data will be used to drive custom applications and data pipelines. So the challenge here, again, it's that golden ratio, the three-way trade-off between scale, cost, and performance. Other solutions often try to address this by simplifying the problem, by throwing away the raw data and just retaining some kind of distilled metrics. But this is exactly the approach that hamstrung us when we were investigating the index problems on Google Drive. And we knew that if we really wanted to make a difference, we needed to find a way to keep all of that raw data, but process it much more efficiently than existing architectures. And we came up with a handful of kind of new architectural directions that were going to enable us to accomplish that. The first was to dispense with indexing. Many solutions, existing solutions, are built on a keyword index, or if not that, then some other kind of index. Indexes add a lot of cost and overhead to build and maintain that. And they're really not always that helpful in observability and event data use cases. Keyword index in particular was originally developed for document retrieval. It's great technology for things like, out of 1 trillion web pages, find me the 10 best match for this keyword. But there's no 10 best in observability. There's no show me the best 10 times my server crashed or the best 10 times we indexed a document. The use cases are very different. The indexes, expensive as they are to build and maintain, don't necessarily actually improve your query performance very much or at all. The second departure was to design an aggressively multi-tenant architecture. So many solutions, whether they're on-premise or hosted, divide the computing resources into across customers, so that each customer only has access to some relatively small pool of resources, typically sized to correspond with the normal everyday usage of that particular customer. And we designed our system to run one single pool of resources shared by all customers in a given region. And this really allows us to get vastly more utilization, higher utilization of the resources and bring more horsepower to bear. So we run this as a single service. The third departure is something we call horizontal scheduling. And the idea there is that when a user initiates a query, we distribute data and we distribute that query across every node in this multi-tenant cluster. So that one individual user has access to every CPU core that we own. Other solutions typically will wind up processing multiple queries in parallel. So they receive a query, a few servers start working on it, another query comes in, some other servers start working on that. And you've got a lot of things going on at the same time, each progressing slowly. With horizontal scheduling, we can devote the entire cluster to a single user query, and 9 times out of 10, that query will complete before the next query from some other user has even arrived. The next departure is it's a very cloud-native architecture. And one of the key points of that is that we really leverage the availability of highly scalable cloud-based object storage, such as S3. So we store all of the data in S3, and then we have this separately scalable set of compute nodes that can process that data. And finally, we have separate pipelines for processing ad hoc queries versus repetitive queries. And you get a lot of each type in observability. Repetitive queries are things like dashboards and alerting rules, where you have the same query that's going to be issued over and over again. Maybe you're checking periodically to see whether an alert ought to trigger. And so we process these repetitive queries in a separate system that I'll talk about. Over 90% of the queries fall into that category, and this frees up the main cluster to make more resources available for that horizontal scheduling. So we built a completely custom event processing pipeline based on these principles. Data flows into the system into a collection of what we call column nodes. And we call them column nodes because the data layout within this system is columnar. We take advantage of whatever structure is available in the event records, and we built a parsing engine that can add structure to the messy stew of log files and other kind of stuff that shows up in an observability situation. So we're able to add structure to that data, which we then place into a columnar data layout. This is one of the techniques that we use to provide efficient query processing without having to spend computing resources on an index. The columnar layout allows us to reduce the amount of data that we're examining for any given query. That data then, as it accumulates, is packaged up into an efficient file format and stored in S3. And then to execute a query, data may be cached in these column nodes. And if it's not cached, then it's retrieved on the fly from S3. Now, this is one of the places where we really take advantage of the multi-tenant architecture and horizontal scheduling, because when we need to retrieve data from S3, we can do it at just astronomical rates. If there are 1,000 files that need to be retrieved for one query, we can retrieve all 1,000 files simultaneously because, again, we're able to use every CPU core and the full network pipeline of every one of these servers just to execute that one query. So in a fraction of a second, data is pulled out of S3 and is immediately available for parallel processing. Then a copy of all the data is fed into a separate system that we call the summary service. And this is responsible for those repetitive queries, the alerting rules and dashboards and so forth. And actually, over 90% of queries wind up being processed by the summary service, as I mentioned. So the column nodes really remain available for the unusual queries, the ad hoc exploration. The net effect of all of this is that 96% of all user-initiated queries complete in less than 1 second. This is across our entire production workload, whether somebody is looking at a megabyte or a terabyte of data. 96% of the time, that answer is going to be back on their screen in less than 1 second. This is based on all of these principles working together. And finally, all of this is managed by a system called the query coordinator. So the query coordinator examines each query to see whether it whether it can be processed by the summary service. If not, then the query coordinator is responsible for distributing this across the horizontally scheduled cluster. And it uses different strategies to execute each query in the most efficient way to finally bring back to that 96% statistic, 96% of queries complete in less than 1 second, get that answer back to the user who needs it. So that is the Scalyr architecture. We call the resulting solution the Event Data Cloud. And it's designed to meet the needs of modern applications running in the cloud, in Kubernetes, all their complexity, serve all the needs from observability to analytics, anything you need to do with your event data. It's designed to replace solutions like Elasticsearch that struggle with that golden ratio of cost, scale, and performance. And if you'd like to learn more, head on over to Scalyr.com.